Alright, in this video we're going to take all the physics skills that we've learned so far and use them and solve this problem. We're going to have to use Newton's first law, Newton's second law, and Newton's third law of motion and also to solve this problem. So let's get started. It says you're pulling a 30 kilogram sled with a rope that forms a 36-degree angle with the horizontal. If you pull with a force of 85 newtons and the coefficient of friction is 0.25, what is the acceleration of the sled? Okay, and like always with these force problems in physics, you always start with a free body diagram. So we know that there is a force of the force of gravity that is equal to its mass times the acceleration due to gravity. So we know that the mass of the sled was 30 kgs. So we're going to take 30 and times that by 9.8. Okay, so 30 times 9.8, and that's equal to 294. So equal to 294 newtons. And that's the force that gravity is pulling down on the sled. Okay, we also know some other forces. It says if you pull with a force of 85 newtons, okay, you're pulling on this rope. So the rope is connected to the sled. So that force in this rope is a tension force. So tension is equal to 85 newtons. 85 newtons. And that force is at this angle because it says you're pulling it up at an angle of 36 degrees with the horizontal. If you look at where the rope connects to the sled and you were to draw a horizontal here, let me do my best to draw a straight horizontal. This 36 degree angle would be this angle right here. The angle that the rope makes with the horizontal. Okay, and then we also know some other forces exist. We know that the sled is not accelerating up and down, so it's on the ground, so there must be the force that the ground puts on the sled, and that's the normal force. And we also know that if you're pulling it to the left, that there's going to be a force that opposes motion, and that force is the force of friction. So force of friction. And we also know that the force of friction is equal to mu times the normal force. And it told us in the problem that mu is equal to 0.25. Okay, and so I think we filled out all the forces so far that at least we know at this point. And you've got to be careful. You might be tempted to throw this 294 newtons of force from gravity up here for n, like we've been doing for some of the problems in the past. But that won't work with this problem, and let me tell you why. We're pulling this sled at an angle. We're pulling it with a rope that's at an angle of 36 degrees from the horizontal. So you're pulling it up. So the normal force is really the force that the ground puts back onto the sled, and it's equal and opposite. It goes back to Newton's third law. It's an equal and opposite force from the force that the sled puts on the ground. And so because you're pulling upwards at an angle, the force that the sled puts on the ground is not going to be this full 30 kilograms of mass. It's going to be a little bit less. And so to figure out what it will be, we're going to use Newton's first law. We know the sled is not accelerating in the up and down direction. And so all the forces down, which is from gravity, which is 294 newtons, has to equal all the forces that are present in the upward direction. And we know that the normal force is going up, but there's also this component of tension. And so if we draw this component here and make a right triangle, this component of tension would be T sub y. Again, because it's in the up and down direction, or the y-axis. And this component of tension down here, this side of this triangle, I'm going to call T sub x, because it's the component of tension that's in the left and right direction. Okay, and we can use Newton's first law to solve for T sub y, which is the component of tension going straight up. And so let's do that now. If there's 294 newtons of force going straight down, we know that the total force going up is 294 as well. Okay. And so if that's total, the total force going down, we can set that equal to T sub y and the normal force. Okay. And so now all we have to do is to figure out what T sub y is, and we can do that using the trig function because we have an angle, we have one unknown side, but we do have another side that we know. So let's use trig to figure out what T sub y is. So if we look at T sub y, it's the side opposite of this angle, and we have the hypotenuse. And so if you remember back to our trig functions and the mnemonic we learned, SOHCAHTOA, we have an opposite and a hypotenuse. And so we're going to use the sine function. So the sine of 36 is equal to the opposite, which is T sub y, divided by the hypotenuse, which is 85. Okay. And so to solve for T sub y, you take 85 and times it by both sides. And so 85 times the sine of 36, and I'm getting 49.96. Let's just say 50.0. So let me write that up here as well. 50.0 newtons of force. And that's going up. And so we can substitute in for T sub y 50 right here. And then we can use algebra just to solve for this missing variable n. To do that, we'll subtract 50 from both sides. So we'll take 294 minus 50, and that will give us that n, the normal force, is equal to 244 newtons of force. So I'm going to put that in for the normal force, 244 newtons. Okay? And so everything down, which was, to review this, everything down was 294 newtons, and everything up, with our component of tension in the up and down direction, which was 50, and then the normal force being 244, we know that the forces have to balance here because the sled is not accelerating or moving in this up and down direction. So that's using Newton's first law again, just to review that, to solve for the normal force. Okay, now to continue on with the problem, we know that he's pulling the sled to the left, but we don't have a force that's strictly in the left direction yet, but we do know that this tension sub x is a force that's going in the left and right direction. It's going to the left. So let's use our trig functions to solve for T sub x as well. We know that T sub x is the side closest, and we have the hypotenuse. So this closest side is called adjacent. So let's use cosine in this case. So cosine of 36 degrees, and that's going to be equal to the adjacent, which is T sub x divided by your hypotenuse, which was 85. And so again, we are going to take 85 and times it by both sides. So 85 times the cosine of 36, and I'm getting that T sub x is equal to 68.8. So 68.8. And so if we put that force in up here as well, 68.8 newtons of force going to the left. And so now we can go back to our problem and see what it's asking us to solve for. We have almost all the forces. Well, I guess we could we could figure the value of our force of friction. Let's do that right now. And so our coefficient of friction was 0.25. So we're going to take 0.25, which it told us in the problem, and we're going to times that by the normal force, which was 244 newtons. So 0.25 times 244 is equal to 61 newtons. And so the force of friction here is 61 newtons. And so now we have all the magnitudes of our forces, and we can go back and solve the problem. It wants us to find the acceleration of the sled. And whenever we see the word acceleration, remember we think Newton's second law, which was, let me switch colors here to see if we can see it a little bit better. So whenever we see the word acceleration, we think Newton's second law. So I'll write that over here, which is force net is equal to ma. Okay, we know the mass of the sled, which is 30, so I'm going to write that in, 30. We don't know the acceleration yet, so I'm going to keep that as a. And we can figure out the force net. We know there's not a net force going up and down. Those forces are balanced. The sled is not moving up and down. But we know there could be a net force left and right. If we look at all the forces to the left, the only force that's strictly to the left is this T sub x, because that's the component of this tension that is going in the left and right direction. And then we also have this force of friction, which was 61 newtons to the right. And so if we take all the forces to the left, so 68.8, and we subtract off what the force of friction was opposing it, which was 61 newtons, so minus 61, and we set that's going to be our force net. So 68.8 subtract the friction, which was 61, and I'm getting a net force of 7.8. So let me write this down, 7.8 newtons to the left. And we're going to set that net force equal to ma, which was 30, its mass, times the acceleration. And so now we have an equation with just one single variable, our acceleration. And so if we divide this equation by 30 on both sides, so 7.8 divided by 30, and I get that acceleration is going to be equal to 0.26. And the units for acceleration, if you remember, are meters per second squared. So we want to include that with our answer. So if you pulled that sled at 85 newtons of force at that angle, the sled will accelerate at 0.26 meters per second squared. And so, yeah, we used a lot of our skills that we've learned in physics so far, and we saw all of Newton's laws in action there. So hopefully that helps you. I've got one question for your video physics that's similar to this. I just changed it a little bit. So here's your, let's go to the next slide. Your video physics assignment will be to solve this one question. Remember, if you get to a part where you get a little bit confused with the concepts, go back in the video, re-watch it, and if you're still confused, stop by at any time. You're welcome anytime. So good luck. I'll scroll through your questions slowly so you have time to pause it and solve the problem. But yeah, good luck.